the normal distribution. Here's a plot of the probability histogram for a binomial distribution for which n is equal to 100 and p is 0.5. In other words, the probability of x heads in 100 tosses of a fair coin, where x runs from 0 up to 100. Of course, the peak, as you expect, is around the value 50. You should notice the characteristic bell shape of this histogram. And on this slide, we've plotted a similar probability histogram with p equals 0.3, same value of n is equal to 100. And you'll notice it has the same shape. It's shifted somewhat to the left, but otherwise the shape is similar. If we now look at a Poisson distribution with a large value of the parameter, say 50, and plot its probability histogram, once again we see this characteristic bell shape for the histogram. And this is true as long as the parameter value, mu, 50 in this case, is reasonably large. We don't expect that shape when mu is very small, like 3 or 4, or in the binomial distribution when the parameter n is very small, like 5 or 6. There is remarkably a function which will fit quite closely all of these probability histograms. The functional form of this may seem complicated at first, but if you construct a density function by exponentiating something, that's a device for ensuring that the number that you end up with is positive. And if we choose a quadratic function of x in the exponential, then we end up with exactly this form. F of x equals 1 over sigma times the square root of 2 pi. That's simply a constant out front. E to the power x minus mu squared over 2 sigma squared. Once again, what appears in the exponential is a quadratic function and is well defined for all values of x between minus infinity and plus infinity. Indeed, what appears in the quadratic is finite, so e to the minus that is some positive number. On this slide, we've plotted a function of that form together with the Poisson histogram, probability histogram. This is the single most important continuous distribution in all of statistics and its applications. It's often referred to as the normal or the Gaussian distribution in honor of its discoverer, a German mathematician in the 19th century called Carl Friedrich Gauss. A random variable x defined on the whole real line, minus infinity up to plus infinity, is said to have a normal distribution if the PDF is of the form a constant times e to the power minus x minus mu squared over 2 sigma squared, where mu is some value between minus infinity and plus infinity, and sigma squared is some positive value, the parameters, these are the two parameters of the distribution. The constant out in front turns out to be 1 over sigma times the square root of 2 pi. But it's the other term which determines the shape, that bell shape of this function. We'll see in a little while that those two parameters, mu and sigma squared, have a meaning in terms of the moments of the random variable. In fact, the expected value of x, if x has this density, is mu, and the variance of x, if x has this density f of x, is sigma squared. So what happens if I change the parameter mu and hold the value of sigma squared constant? On this slide, we see 3 such density functions, and you can see that the value of mu, when it changes, simply moves the density function to one side or the other. For example, the blue curve is mu equals 0, the red mu equals 1, and the green mu equals 2. Indeed, the center of the blue curve is at the value 0, of the red at 1, and of the green at 2. So mu denotes not only the expected value, but the center or the peak of this density function. What happens if we hold the parameter mu constant and change the parameter sigma? You see here a blue curve corresponding to sigma equals 1, a red curve, sigma equals 2, and a green one, sigma equals 3. Evidently, the curve stays in the same position, but it's spread more as the value of sigma increases. It's less peaked, it has more weight in the tails, in the extreme ends of the distribution, when sigma is larger. The normal distribution was discovered by the German mathematician Johann Carl Friedrich Gauss, a mathematician of extraordinary talent. And although he was born to poor and illiterate parents, parents who were unable to register his name on birth. He was educated, the discoverer of many different results in mathematics and probability and statistics, including Bode's law, the binomial theorem, the arithmetic geometric mean, the prime number theorem. He discovered the regular 17gon, and he used least squares methods, unknown to that point, to predict the position of the dwarf planet Ceres so it could be observed. He also developed the fast Fourier transform, essentially 1.5 centuries before the work of Cooley and Tukey. But for our purposes, his most important contribution was that the normal distribution was an approximation to the binomial. On this slide, you see the standard normal probability density function. By standard normal, we mean the parameter mu is equal to 0 and the parameter sigma is equal to 1. The cumulative distribution function of the normal distribution is, of course, the integral of the probability density function up to the point z. Unfortunately, analytic integration of this function is very difficult. And for those purposes, we use either tables or, increasingly, a computer program or calculator to evaluate the normal cumulative distribution function. For example, in this figure, you see the area under the standard normal probability density function between the values -1 and +1, that area being around 68%, with about 16% of the area below -1, and exactly the same amount, about 16%, above the value +1. If, again, we look at the standard normal density and compute the area between the values -2 and +2, the area is substantially higher. In fact, it's 95% roughly, a little more than 95% of the total area of 1, with about 2.3% below -2 and another 2.3% above +2. As a rule of thumb, you can say about 95% of the area under a normal curve is within 2 times sigma of its mean, mu equals 0. And you'll notice in the lower figure, if we calculate the area between -3 and +3, that area is very close to 1, something like 99.7%. So although theoretically a normal random variable can take values at -4 or +4 or above 5 or below -5, the probability of these values is extremely small. For practical purposes, this is impossible. There are many observations which are often considered to follow the normal distribution. For example, the heights or the logarithm of weights of people or of objects, the size of manufactured items, the errors in a physical experiment. These are often assumed to follow a normal distribution. They are both reasonably close on the one hand, and on the other hand, the assumption of normality makes calculations and estimation much easier. In finance, returns, for example, the percentage changes in stock prices, or in a currency value, or exchange rates, or interest rates, these are often assumed to be normally distributed random variables. In fact, in this histogram, you see the frequency histogram of changes in the Standard & Poor's 500 returns over an extensive period of time. And once again, you'll see a typical normally distributed shape. It's peaked in the middle, it goes down at either end, and it's roughly symmetric, although you will see some returns that are much more negative than you'd expect under the normal assumption. The normal cumulative distribution function. Of course, the value of f of x is the area under the probability density function to the left of x, as demonstrated in this illustration. And we've given those values for certain values of x in this very rudimentary table. For example, when x is equal to 0, the area to the left is 1/2, and that follows by symmetry, because the probability density function is symmetric about the origin. When x is equal to 1.0, the area to the left is 0.841. When x is 2.0, the area to the left, 0.977, and so on. There's a more detailed normal CDF table available in your notes, illustrated here. You'll notice it only gives the value of f of x for values of x greater than or equal to 0. We'll give you a few examples of how to work this table. Suppose, for example, I want the value of the cumulative distribution function at x equals 1.1. I look at the value 1.1 on the left margin of the table, and I look below the value 0, since we're looking for 1.10 on the top margin. The entry in the table is 0.8643. So that's the CDF, f of 1.1. What about f of 0.6? Well, that's almost the same argument. Look opposite 0.6, below 0, and we see 0.7258.